Hmm. That is the Hmm. Hi. Oh, hey. Sweet people here. And now, hello. How's it going? Trying to get this where I can watch the chat and do presentation at the same time. It's not really working. I think it should be able to do that. But, here we are. No Arthur today. Oh, I should change that. Hmm. Check. Well, hmm, with just one person watching, I think that's me. Let's see. Here's something. Look at live. Everything's fine. Is it just because of the healthy stream? Is that why that's going on? I don't know. Oh, that's me. That's me. I'm watching me. Hmm. Huh. Okay. Cool. Uh, oh, the chat. Chat. Oh, chat. Love. Alright, well, I'm here. We can be here. What can we put on in the meantime? Oh, right. Let me just see. It doesn't tell me how many people are watching. Oh, there's 3 people here. Whoa! Hi, welcome. Wait, I scared him off. Who grants that? Like 1,000 outrights. That would be like. So, mm, Oh, hello. Welcome. If you have any questions, feel free to ask them. I'm not really entertaining other than that. Just doing my grading. Okay. Hi. On the test tomorrow, so it's multiple choice and it's AP alike. So we're talking very similar to the test that I gave you early in the year. And you know how a lot of the questions on the most recent test didn't need a calculator? There's going to be stuff like that. But let's see if I can scare up some AP alikes. There we go. Yeah, we'll do that. So we're talking something like there'd just be some simple, straightforward, like integral, indefinite integral, like saying integral from 1 to 2 of 4x to the third minus 6x dx, and you'll be expected to do something like that, right? So, basic stuff like that, where you're just doing a straightforward definite integral. When it comes to more complicated stuff, definite integrals, also like just derivatives. 2x minus 3. So it's like if f of x equals x square root of 2x minus 3, right? What is f prime of x? So that's like the simple, straightforward part. And then, we're going to talk with stuff that, so you know how to do integrals, you know how to do derivatives. But like, it's going to test your knowledge in strange ways, right? So here's one that's kind of interesting, right? So it won't be just that, it'll be things also included. So I'm going to go ahead and assume you can kind of do something like this or something like this at this point. But some things that might be a little bit trickier, right? Where we start using variables and how do you know, or letters to stand in for constants, and how do you know how to do these things? So it's like, what if the integral from a to b of some mystery function f of x dx equals a plus 2b? And I'm going to check to make sure I got that right. Yeah. It's like, so we know this thing about it, then what does it mean if we take the integral from a to b of f of x plus 5 dx? Right? Oh, wait, what the heck? Oh, weird. Oh, sorry. I will fix that. Yeah, that'll work. No, I'm not really a historian. I know something about history. Welcome to a new thing. I'm more math, but I guess you can ask me anything and I'll try to answer. Alright, so if we're doing something like this, right? you just have to kind of like go with the flow, right? For whatever reason, this integral equals that, right? And you just have to rely on what you know about integrals, right? So we know that any integral, if we are separated by plus, we can separate it out. So it's like this integral, or sorry, this integral is equal to the integral of from a to b of f of x dx plus the integral from a to b of 5 dx, right? So, you know, you just kind of have to, there's an art in being stupid here, right? The constants are there to trick you, but if you just kind of proceed forward confident that it's going to work, it will work. Because once we separate it out like this, we know what this is. This is going to be a plus 2b. 2b. And once we do that, we know what this one is, because like integrating a constant, that's pretty easy. It's just going to be 5b minus 5a, or 5 times b minus a, however you want it. So 5b minus 5a. And once you have it like that, you just group the like terms. 2b plus 5b equals 7b, and then a minus 5a is negative 4a. Right? So something like that. Dare to be stupid. In something like that. Don't let it intimidate you. Simple things where you take the derivative, being able to recognize when they're asking you to take the derivative of something. So if it's asking like, so if you have f of x equals negative x to the third plus x plus 1 over x, right? And it asks you what is f prime at, I want to say 1 at negative 1, right? So, you know, try not to fall into the first month habit of like, do I put the number in first or do I put it in second? If you put it in first, you'll end up with 0, right? So you take the derivative first. It's negative 3x squared plus 1 minus 1 over x squared. And then you put in negative 1. So you get negative 1 squared plus 1 minus 1 over negative 1 squared. This becomes negative 3 plus 1 minus 1, or negative 3. Right? Take the derivative first. Do whatever you need later. I chased Bilby out, I guess. Can you solve an equation? Maybe I'll ask another question. Anyways, you'll need to know the consequences of concave up, concave down, how those relate to the derivative. So you'll be able to, you know, the words, sorry, you'll be able to translate things into words, right? So if you have something like y equals 3x to the fourth, third, minus 24x squared minus plus 20x squared plus 48. Not really matter. And it asks, when is this concave down? So it kind of expects you to see like concave, so we're looking at the second derivative, and it's down, so we want to see y double prime, the second derivative, is less than 0, right? And so being able to do that, so it's like if y is this, then dy dx is 12x to the third minus 16 times 3, 30, 48 squared plus 48x And then the second derivative, d squared y over dx squared, is going to be 36x squared minus 48 times 2, 96, x plus 48. And then, you know, going in there and being confident that you can just kind of like solve this. We're looking for its concave down. We're looking for when it's less than 0, so we want to focus on when it's equal to 0. Not everything's divisible by 36, but everything's divisible by 12. 3x squared. 48 divided by 6 is the same as 24 divided by 3, which is 8. Yeah. Yeah, that's why it doesn't, so the derivative of 48 up here, there's no corresponding here. This 48 comes from this, and then the derivative of 48x gives us a new 48. That's fine. No, like, sometimes being stupid is desirable in the AP calculus tests. Don't get me wrong. And so you have to factor here. Well, you don't have to factor. You can use the quadratic formula, but this is geared up so that it's well factorable. 3x, I need to do 3x to multiply 2. And since it's less than 0, I know since it's quadratic, it's going to be less than 0 between these two zeros. And so it's like, oh, it's concave down when x is between going to be 2 and 2 over 3. Well, let's see. Let's see if there's another like semi-spicy one. That's fun. You know, if you're doing integrals, and just like be able to worry about like different formulas. Oh yeah. Just because that this is the no calculator doesn't mean that there aren't graphs and being able to interpret graphs. Related rates. Could I do a related rates? Yeah, I could probably find a related rates pretty easily. Hopefully. I haven't actually checked the test to make sure that there's a related rates problem on there, which maybe is not the greatest for me, but whatever. Excuse me, the screen's going to shake a little bit because I need to get my actual book out. Right? Yeah. Maybe it's not a great idea, but I used my book to prop this up so it gets a good angle. Differentiation. Optimization, differentials. Technical difficulties. Yeah, let's do some related rates. And just so you know, related rates, while they are important, it's not like there's a lot of things to ask about, and they kind of focus a lot on just the basics. So, you know, you're not necessarily guaranteed a related rate problem. So let's make sure. Oh my, I'm still in the frame. Nice. All right. So half the battle of related rate problem is just kind of like understanding the text, because there's often a lot of text. Well, that's a good one. And why not? So say a good related rate problem is we've got like a space launch. And then we're following the space launch with a camera that's functionally speaking on the ground, right? And so the spaceship launched completely vertically, and then we're just kind of watching it with this camera, right? So you need obviously like some information. So in this one, the camera is 2,000 feet from the launch pad. We've got the if we call this S, the distance above the ground. I don't know why they call it S, but you know they're going to use weird letters for it. So if you have S equals 50 t squared, where t is time after liftoff, right? And then we ask, what is the, we'll call this theta, the angle. It's like, what is the rate of change of theta, 10 seconds, liftoff. Right? So that requires a little bit of setup. Always when you have a related rate problem, take inventory of everything you know, right? And keep in mind the things that you just want to find out, because you don't want to find out anything extra, right? So what do we want to know? We want to know this rate of change. Anytime you see rate of change, that's a derivative in terms of time. And it's of theta, right? So we need something that relates our theta to the stuff that we actually know what's happening, right? And well, anytime you have an angle on a triangle, you're going to use a trigonometric function, right? In this case, since we know something about the opposite side and we definitely know something about the adjacent side, we know that the tangent of theta is going to be equal to opposite, which is S, over adjacent, which is 2,000 feet, right? Right? So it's like, oh, that's nice. Things that we might want in this case, we might want to know what ds dt is, because that seems interesting. Which we can do by taking the derivative of that, and we get, oh, it's 100t. 100. Right? So it's just kind of like assembling what you know. And then the central feature is like once we have something that relates what we want, like what we know to what we want, which is in this case this, we're going to take the derivative of everything in terms of t, which looks a lot like taking the derivative implicitly. We look on this side, take the derivative tangent, well that's secant squared theta, and then you have to remember the chain rule. We're taking the derivative in terms of t, so you get a d theta dt, right? which is good. We wanted d theta dt. It's nice that we saw that. On the other side, this is just a constant. So, and this is just a number times a constant. So we can just kind of, this becomes ds dt over 2000. Yeah. Right? Well, we know a ds dt. It's 100t. This is kind of a problem at this point. So we're going to have to go back to the drawing board in a little bit. But suffice it to say, this is 100t. We know t is 10, because it's 10 seconds after liftoff. So we get secant squared theta d theta dt equals 10 times 100 is 1,000 over 2,000, which is 1/2, which is nice. My pen is not necessarily registering today. There's still problems. We obviously have the secant squared theta, and we wouldn't like that. So we can change that where theta dt equals 1/2 cosine squared theta. And then we come to kind of like the last part where like cosine. Cosine is adjacent over hypotenuse, right? And we have to go and kind of just do some work to figure out what this all is, right? 50t squared, 50 times 100, this is 5,000. Yep. So if that's 2,000, this is 5,000. We can think about that 4, 25 square root. Like the square root of 29, 2, 3, 4, 5, 6. So it's like 1,000 times the square root of 29. I think my pen is kind of failing. Oh, but it gets squared anyways, so no big deal. How did I get that? So one of the things, especially if these are the same order, like this is 5,000, this is 2,000. 5,000 times 2,000. Since they're the same order, right? We can kind of ignore the thousands. Know that whatever we get is multiplied by 1,000, and think of this as just 2 and 5. 2 squared is 4, 5 squared is 25. Sorry, 4 plus 25 is 29, so that's why we have the square root of 29. But we actually need cosine squared, so that's kind of nice, actually, for us, because we get 1/2 cosine 2,000 over 1,000 root 29 squared. But how did I get 5,000? Oh, sorry. Yeah, we know it's 10 seconds after liftoff, right? Well, we know this height is 50 times t squared. So 10 squared is 100. 50 times 100 is 5,000. Over here, these conveniently cancel out a lot. And so you're left with, when you square the square root of 29, it becomes, if you'll excuse me because we got kind of crowded there, 4 over 2 times 29, which is equal to 2 over 29. And then when you have that answer, you re-express it in, maybe make a unit, radians per second, right? Because everything's a second. But yeah, like all of these follow the same procedure, and I don't want to like. That one is honestly fairly hard. So it's just kind of like, what do you have? What do you know, right? What's one that I haven't asked you before? Did I do the pipe? Okay. All right, I'll try to do another one pretty quickly. Oops. So say you have a building, and then there's a pipe, and like you're winching the pipe close to the building. And the building is 12 meters tall, and the pipe is 12 meters long. And then this distance is just kind of s. And so we're saying, oh, we're going to pull it in at a rate of, 0.2 meters per second, right? So when you express that in this, it's like, oh, this is changing since they want to pull it in. S is changing at a rate of negative 0.2 meters a second, right? Some of this may be done for you, some of it may not. And they're find rate of, let's say, vertical change. Of the end of pipe. When y is 3. Or sorry, y equals 6. So imagine like if it's 6 meters up, right? How much more up is it getting? What's the rate of up in this case? And the biggest thing is just kind of like finding relationships here, because it's like not entirely clear what's going on. And so you want to kind of like have a relationship that involves s, which we want to know, and something that's like vertical, right? And for this case, I see a right triangle. I incidentally drew it. So I'm going to use this rather than like the true height, because that seems a little bit complicated for me. I'm going to label this like, since it's not the true height, I'll just call this x, right? So this is like how far it has to go. And then we need a relationship between s and x. This one's kind of annoying. Maybe I shouldn't have picked this one. This is actually more complicated now that I look at it than the one. Let's make this x. This is y. That, if we need it, is 6 minus y. Yeah. It's probably bad form to give up on the thing you chose, just because, like, I'm very clear that this is more complicated than you will actually get. Also, I should check to see who's around. It's 4 people. Sorry, 12. So, 1 minus 1 squared. Oh, this is actually probably fine. So that's kind of our relationship. Vertical change of the pipe. So that's going to be dy dt. Damien? Which Damien? Anyways, we're doing this. X is kind of our problem child, right? We don't like having this X around. IDK. Okay. So, but we're going to use this other relationship here, that y squared plus x squared equals 12 squared. So, of course, x squared equals 12 squared minus y squared. Oh, that turns out really convenient. See? Do you have Snapchat? Oh, okay, so you're just a rando. I'm not giving out Snapchats. Why does it say 12 minus y? Because I renumbered it and I messed up the first time. So this quantity, which I'm calling y, which is the height, it's going to change over time. So I'm calling it y just because it's simpler. And then that the remaining is going to be the whole height, which is 12, minus y. And that's why it's 12 minus y. I kind of messed up with 6 minus y. So now that we have this other thing, we reset. Oh, this whole thing, when we substitute, becomes 12 minus y quantity squared plus 12 squared minus y squared equals s squared. And finally, we can get some actual resolution on here because we finally have something that we can just take a derivative of, because it's only two variables. If you feel like it, and I kind of do, now, on second thought, I don't. So we're just going to take the derivative of everything in place, right? So this becomes 2 times 12 minus y, and since it's a minus y in there, it becomes negative 2. This goes away, and this becomes minus 2y. And then each one has a dy dx. And on this side, we have 2s, s, ds. I'm just messing up all over. This is supposed to be dt. And so now, it's ugly, right? But it's all mostly stuff we know, right? We know that y is 6. So in this case, we get, since y is 6, 12 minus y is, of course, also 6. So we get negative 12 dy dt minus, again, y is still 6, so 12 dy dt equals 2s. S is a little bit of a problem. We kind of have to go find s, because we never bothered to figure out what it was, but luckily we have an expression that gives us s squared, and so we can find just s with that. 12 minus y is, of course, 6. 6 squared is 36. Plus 144. And then y was still 6, so minus 36 equals s squared. Man, all of these just turn out rather convenient, so s is apparently 12 at this case. Oh, of course it's 12, because the equilateral triangle. So that equals 24, and then dsdt is negative 0.2. That's negative 24. That's amazing. And then when you do a bunch of algebra, right? I'm going to leave that off. dy dt, that's what we wanted, ends up as just negative 0.2. Convenient like that. And this kind of shows the thing where related rate problems are both illuminating and not illuminating at the same time. Like I could do a million problems, and every problem I do wouldn't necessarily help you on the next problem. But there is a procedure I'm following, right? And that procedure is not one you're used to doing, because it involves taking everything I know about the situation, just kind of blurting it out and seeing what I can fit together, right? I didn't have an idea of how this was going to be solved at the start, and I kind of honestly wanted to punt it earlier when I thought like, oh, this is gonna suck. But I kept throwing the relationships out of there and knowing that I had to get it down to two variables, and then I got it there and everything simplified, right? And that honestly has a lot of AP type problems are designed to kind of like explode and then condense down, right? Where it's just much more simple. I mean, I got a million related rate problems. I could just keep doing related rate problems if that's what you want, but I guarantee on the test tomorrow there's not going to be more than one. Like, if there even is one. So if you have something else that you'd like to see, by all means, ask and you shall receive. I think this needs its battery changed. I think that's what's going on. But in the meantime, rotate a volume around x equals y. Yeah, I can do that. That's an extremely unusual rotation, but sure. I highly doubt that you'd see something like that. Well, let's see. What would be a good region for that? To rotate. I don't have to rotate cleanly. Do you want a hole in the middle, or do you want a solid? Let's start with a solid. Rotate something around the line x equals y. Okay. See if I can find something pre-made, because whatever is most complicated. I appreciate you trying to do that, but honestly, like, and I don't say this flippantly. The AP test, its difficulty comes from the fact that everything is on the table. If they're going to ask you to do rotation, it's not going to be. It's typically not going to be a particularly difficult one. You're going to have it around. It's going to be stuff that's rotated around. It was on a practice test? Well, which practice test? I want to see. Show me this practice test if you can. If it's not important. I mean, no, I would love to see this. It's just rotate around the line y equals x. One I found. Yeah, I know, like, all the practice tests, did you get it from like Khan Academy, or did you find like one of the officials? Yeah, I'd love that. Oh yeah, I know you were on the official ones. So a note to anyone else who's like around here. I'm using I'm using released material, and released material is released, so it's out there. It's entirely possible that if you've been like looking up this stuff on your own, you could conceivably have just seen the entire test, uh, which is maybe information that's more dangerous than not. But here we are. Like, my textbook doesn't even have rotating around the line y equals x. Maybe it's got something in shells. Let's see. Let me think of something. It's around the line y equals x. It has to be a very strange. I could. Yeah. That's. And I hate to say it, but I feel like that's maybe more likely. Just because the trying to define a proper variable when you're rotating around a diagonal line just gets. Watch it be on the AP test. No, I'm serious. Like, it's not going to be on the AP test. Like, I would definitely bet against that. There's going to be solid volumes of rotation, certainly. Probably one, but that's the thing. Like, I hope you did too. I'd like the challenge of something around line y equals x, but that's the kind of thing that I'm not going to make up something on the fly that I would guarantee that I'd be able to do. With that, there'd be too much of a chance of me giving myself an impossible integral problem. So I was just making it up. But yeah, you're gonna see volumes of rotational solids. It's gonna happen. So while Emma works on that, we're just gonna do a normal volume of rotational solid. So let's say we've got with a hole. Okay, so let's say we have a region bounded by y equals the square root of x, y equals 0, which you may know as the x-axis, and x equals 4. So when we graph that, this one's going to be a slightly boring hole right now, but we can do other ones. Just like that. And so let's say we revolve that around the line x equals 6. Right, so it's like, oh, the line x equals 6, that's a vertical line. And so when we revolve it around there, we get this kind of symmetric thing like that, right? Like I said, this is a boring hole. We can get ones with more interesting holes after this, but it's like, start with the basics. Because our central hole is going to be a cylinder. So, cool. So that's a cylinder. The biggest problem with this is we're going to have to redo our variables a little bit, because when we do the outside of this rotational solid, right? And we think about like, oh, if we're doing it based on the outside, what is our pancake looking like? Well, the radius is going to be from 6 to this, right? But it's going to be to the like x-ish of that. And since this is like flat, this is going to be in terms of dy, right? So you need to do a little bit of alteration. Luckily, it's an easy alteration because x equals y squared. if we're in this quadrant and all that's good, right? So this one is going to be, the length of the radius, which is from here to here, is going to be 6 minus y squared. Cool. And so the volume of the whole thing is going to be the integral. Our integrand is going to be, I'm going to need pi because it's rotational, 6 minus y squared dy. Around x equals -1. I thought so. But I appreciate thinking about the challenge. I'm not ready for that challenge just yet. Maybe I'll get to it. And then since we switched to y, because it's rotated around this way, we need to rethink the bounds, right? Instead of being from like 0 to 4 or 0 to 6, it's from 0 to whatever this height is. Luckily we know x equals 4, so y equals 2. Right? So that's the volume of the whole thing, and then the volume of the hole in the middle is, of course, the cylinder of radius 2. So that's going to be, and height 2. So that's going to be pi times 2 squared times 2. And so when we chain this all together, it's going to be, and remember, how you do this is different if you're doing multiple choice versus long answer. Because if you're doing a long answer, you want to make really sure that you combine this all together. So it's like, oh, the volume equals, because you get points for having the right bounds. You get points for having the right integrand. Or 8. Right? And then it's only that last point that you get the right answer. So I'm going to square that out. That becomes 36 minus 12. I'll do this properly. So this is the important part. So I'm just going to do that separate. 36 minus 12 at y squared minus plus y to the 4th dy. You do your integration. This becomes, I'm going to put the pi back in because why not? 36y minus 4y to the 3rd plus y to the 5th over 5, evaluated from 0 to 2. And then minus 8 pi, of course. And then it's just kind of like you do some math, you plug in 2. Luckily, since it's from 0, that makes it nice and easy. But it's like, okay, so we have a pi. I'm going to factor out the pi just because it's easier for me. 36 times 2 is 72, minus 2 to the 3rd is 8. 8 times 4 is 1632. 32. And then plus 5/5, 32 over 5. And then we'll have this minus 8. Lump it all together. Why not? And then some fraction stuff, which I'm going to ignore here, just because you're not going to get appreciably better at fractions in the next day, right? All right, so that's that. Yeah. Let's do something with a curve like that. Yeah, that'll work. So we have a region bounded by, so region between y equals do I want to rotate that? Which axis do I want to rotate that around? Yeah. You rotate that around the x, so it helps to draw a picture. Unfortunately, with this one, the picture isn't that great. So it's basically like two things like that. It's a very thin sliver. They intersect at 1, 1. And then you rotate this around. So you get this kind of dumb trumpet, I'm going to call it. It's a dumb trumpet. And so, okay, you rotate that around, and you're like, okay, you need to know which one's the outside. And since you're between 0 and 1, the outside is actually the x squared. Because if you're less than 1, x squared is going to be larger than x to the third. But at this point, like, oh, this outer radius is x squared, this inner radius is x to the third. The volume, since we're rotating pi, integral from 0 to 1 of x squared dx minus pi integral from 0 to 1 of x to the third squared dx, right? And then it's just like, oh, this is x to the fourth, so this becomes pi, and I'm going to lump the pi's together at this point. X to the fifth over 5 minus 6th x to the 7th over 7 evaluated from 0 to 1, right? And so it just becomes pi 1/5 minus 1/7, which is 2 pi over 35. Right? Does that help? How are you feeling about that? How are we all feeling about that? Again, I can do more. Good, you think? I hope so. Right? I hope this does well. And again, if you're looking at previous study materials, I would recommend the earlier tests, like from first semester. You're going to see a lot of overlap with the kinds of questions that I asked there and the kinds of questions that are going to be asked tomorrow. And also, like, again, if you're feeling kind of bold, like, the test I'm giving is out there. I'm not going to tell you which one it is. But, like, all these tests have been released. Like, it's not a secret. And I know, Emma, you were looking at these. So I feel pretty confident that, like, what is this? I'll read. Find a line tangent to the curve. Yeah, sure. Do you want it? Okay, so there's there's like a simple version of this, and then there's a complex version of this. So like the simple final line tangent of the curve is like, let's take some curve, right? Y equals, let's make it a cubic, right? This is probably dangerous of me just making up numbers. Let's make that 8. Right? So it's like finding the equation of a line tangent of the curve at x equals 2. We need two things for the equation of a line, right? We need a point, and we need a slope. If it just specifies an x, and this is the tricky part, if it just specifies an x, we luckily don't have to worry too much. To find the point, we just take our x and plug it in here. Y equals 2 to the third plus 2 times 2 squared minus 8. 2 to the third is 8, so those cancel out, and this becomes 8 again. So our point is going to be 2, 8. Then for slope, we're going to, slope of the tangent line is always the derivative. So we need dy dx is going to be 3x squared plus 4x. We plug in 2. That becomes 12 plus 8, which is 20. So it's just kind of like a big slope. Sweet. And then you're going to connect them up using the point slope formula. The one that you always look at in Miss Hong's room, and the one that's going to be probably closer to what you're going to see on the test, is going to be y equals the y value 8 plus the slope times x minus the x value. So that's in point slope. Since this is multiple choice, there's a chance that you're going to see all your choices in slope intercept, which is no big deal. You just take this and distribute it as needed. So y would equal 8 plus 20x minus 40. So y equals 20x minus 32, right? Both of these are answers. It's up to you to do the algebra to do this. And like, chances are high that this is the kind of final line tangent of the curve you're going to see. It's just like, we specify an x value and we don't really care whether or not, like we don't really care about the specifics, right? It allows us some freedom. Is there one? It gets more complicated, and there's a very specific thing. Yeah, chances are high that's going to be all there is. Oh, you just need a refresher. Okay, yeah. There's a more complicated version. Chances are low that it's actually the more complicated version on the test. The key thing to seeing that it is the more complicated version is in the text. It'd be like, find the equation of a line tangent to the curve through point something. So this is one of those cases, and I just want to point this out. The language, there's a big difference between if you see the word through versus if you see the word at. Okay, because this, if you see this like find the equation of a line tangent to the curve at point this, that means that this is on the curve. And you actually have less work than in the previous problem because it gives you the full point, right? But if you find the equation of the line tangent to the curve through this point, that implies more often than not that that point is not on the curve. Right? And if you have a situation like that, the difficulty spikes immensely because you're in a situation where you have some curve and you have a point that's not on the curve and you're trying to like figure out what derivative hits it, you know? And there's actually probably going to be multiple answers because in this curve that I just sketched out, I can already see there's that answer and there's that answer. And so you're going to end up, if you ever see like through, it's going to be not on the curve, which means you have to solve a system of linear equations, a system of nonlinear equations. Sometime in the process, right? This is very unlikely. This is pretty much a given. You will see more than one of these. You will see this. So when we're prioritizing studying, and we are at the stage where you just kind of have to prioritize what you want to see. You know, if you're studying finding the equation line tangent to the curve, prioritize the at. Make sure you've got that in the bag, right? Don't stress too much about this. Like, unless you're feeling like very confident about everything, and since AP is a comprehensive test, like I really do stress everything. It's not usually worth your time chasing this particular dragon. But of course I can show you that. But I think we're running out of time for me because I'm getting a little tired. Do we have any last questions before, since it's just been the few of us, do you have any last questions before I sign off? All right. Well, thanks everyone for stopping by. It was pretty small, but I think we got a fair bit done. And then I don't think any of you are in physics, right? No, Carla, you're not in physics, but Emma, are you in physics? Okay. Um, I'm thinking of making Monday of next week just kind of a general Q&A where I could field physics questions too. Would you like that? Okay. All right, yeah, I'll do that. Well, thanks for stopping by, and I'll see you guys all tomorrow.
You gonna live stream?